Hi everybody and welcome to another episode, and today we are going to cover meteors in a nutshell. And of course I told you in the first introductory video that I would like to have some small kind of scientific video, maybe just only half an hour or so, where we get a basic understanding of a certain topic. And here I would like to talk about the falling stars, especially with a dedicated focus on the Geminids later on, because the Geminids, they have a peak at between the 13th and the 14th of December. So if the skies are clear, go outside and watch this night meteor stream. But we will understand later in the video where to see them and what to expect exactly. This timestamps you see already in the bottom in the description. You see that we have some kind of scientific overview. I will talk with you using Stellarium, the planetarium software, to give you some insights, also some online tooling, and also later on Universe Sandbox to understand a little bit the origin of the Gemini stream. But without further ado, I would say we switch now to the presentation I just named Meteors in a Nutshell. And the very first initial image you see here gives you already a picture that you have maybe seen already on the internet, or maybe you have even recorded or made your image on your own with a meteor. And we see that some guy called José Pedrero tried to make a picture of the Andromeda galaxy, but during the session, a meteor was photobombing his session, and it created this greenish bluish light and also some brown colors here, basically originally, let's say, ruining this picture, but also making it now very unique. And we see that this kind of stream is, of course, due to the long exposure. For example, the image came, or the meteor came from the top right. You see it increase its brightness here. It was oversaturating the camera all the time. Then it changes color, and then at some point also it fades away. And the different colors already helps us to determine the chemical composition of meteors, which is pretty much fascinating. So even from a simple image, we can already derive a lot of things. Also here, the dust evaporation in the atmosphere between 180 kilometers above sea level, because this is where the meteors appear. Now, second image here as well from the Chile desert, where in a long time exposure we see a meteor coming from a certain direction. And this is also one of the settings properties we can derive from meteors. Even from this kind of simple images, we can of course determine the direction, but at least only the line of thought where it actually came from, but we don't know really the true direction. We will have a look later how to do this exactly. We can compute also the angular velocity and also determine the brightness that is basically correlated to the mass of the particle, although this equation is, I will not put any equations today here, but it's a very empirical one, and it's not really, let's say, verified for now. And also, as I just mentioned, the chemical composition, because nitrogen, oxygen, iron, other elements and chemicals, they illuminate or they radiate in a different color when the meteor is entering the Earth's atmosphere. However, talking about meteors and meteoroids and asteroids, people use these words almost as a synonym, but I would like to give you an insight. What are the differences? Because it's not that trivial, but also kind of easy to understand. Because let's take an cosmic object here on the left hand side. If this object has a diameter of less than 30 micrometers, it's basically cosmic dust. And if it's larger than 30 micrometers and smaller than 1 meter, then it is called a meteoroid. And I just represent it here with a small stone. We will just work with that in a second. So meteoroids and cosmic dust, they are responsible for our meteors that we see, because the meteors, they are between a few microns and also a millimeter in size. The brighter ones have a different name. We will talk about it just in a second. And everything larger is, of course, an asteroid, comet, planet, or what have you, depending also a little bit on the context. Taking this small object here, if it's entering the atmosphere, is then called a meteor. And really talking about language, a meteor from the Greek word originally means something that it's an appearance in the sky. So literally a lightning or clouds are also meteors. They have different endings, but well, nowadays the meteor is a synonym, is a word for these kind of entries in our home planet. If it's large enough, a solid remnant remains, and we find it as a meteorite. And the meteorite, there are several different types with different chemical compositions. And my favorites are the iron one, because if you really cut them open, you apply some acid, you see certain grid pattern structures, the Wittmann-Stetsche figures, they are called in German, I think in English as well. And these are grid structures based on due to the cooling of a hot metal blob in space. But this cooling effect in space is very inefficient. It has to lose heat due to radiation. This is a very ineffective process. It takes thousands or 100,000 of years, leading to certain patterns you only find on meteorites and not on anything else on our home planet. So if you find this thing and you cut it open, it's a very good indicator that it is an iron meteorite, but there are also others like chondrites and what have you. Now, the thing is with the meteors, we have a naming for them, but there are different brightnesses. Yeah, for example, if it's a value, if the brightness is smaller than 3 magnitudes or 4, depending whether it's the International Astronomical Union or the International Meteor Organization. It doesn't matter for now. They define the brighter ones as fireballs, and the magnitude, if you don't know what this is, I also made a video in the past. Maybe let's refresh it also with a science video now. Is something that is the brightness. So it's a logarithmic scale, because our eye perceives brightness logarithmically, and the reference point is the Vega. That has 0 magnitudes, and the faintest star you can see has around 6 or 6.5 magnitudes, and negative values indicate a brighter object than Vega. So for example, Jupiter has -2.7, I think. We have the International Space Station, and also some meteors are brighter, as well as fireballs, also the sun and the moon. But if it's even more brighter, then it's called a bolide, like -14, and a super bolide, -17. But these are really the big ones that leave definitely remnants and maybe also some kind of damage on our home planet. Here again, the both organizations that are responsible for the different definitions, especially the fireball, again, is not really clearly defined. One of the projects I worked on in the past was the Canary Island Long Baseline Observatory. These are 2 cameras on the Canary Islands that have an overlapping field of view at around 80 to 100 kilometers. And this overlapping field of view works then like a huge stereoscopic camera, like a 3D camera basically. So if a meteor flies through there, you can really determine the trajectory and the orbital elements of the particles, which is pretty amazing. And I also worked there on these things during my PhD, also at this very instrument. So this is how the camera looks like. It's embedded in this housing, has a small rooftop that opens and closes automatically when it's raining or when it's in dark and so on. And here for maintenance, it's open during the day, but the camera was very sensitive and it can even take some damage when it is exposed to broad daylight. The big question though is, why are we conducting this kind of science? Of course, on the one hand, you can always say that science is human nature. You really want to understand everything around that. This is our inner curiosity to understand our vicinity, but it has also major technical implications. What you see here, for example, is the Hubble Space Telescope on the right side. That was also set to space, I think, in the 1990s with STS-31 was a space shuttle mission, and also the other space shuttle missions went to the Hubble Space Telescope for maintenance, repairing, and so on. And they repaired also the solar cells. They brought them back to Earth, and there they were analyzed, and we found here different, well, unhealthy structures, let's say. Yeah, so we see here like some good areas of the solar cell, but also here already some kind of specks, also larger cracks or even a hole. And these holes or these damages on the solar cell, they have 2 reasons. The one reason is probably space junk, so the things that we leave in our orbit around Earth, and also the micrometeoroids that are causing the meteors but are also damaging our spacecraft. And the effects, they are kind of severe, although they are kind of tiny. Yeah, if you wear glasses, then you may know, these glasses, mine are now kind of new, so only a few weeks old, so the glasses are perfect. I have very sharp vision. But after 2 years or so, depending also how much I will take them, for example, for outdoor activities, they will get tiny scratches, yeah, from dust, from sand and so on, impairing the visual quality of the glasses. And the same thing happens with our space toys, whether it's the solar cells or the optical cameras. They are being bombarded all the time and getting scratches and damages and are degrading. For solar cells, this leads to less energy, of course. For optical systems, this leads to lower quality. And this thing has also been observed with our James Webb Space Telescope, which is also kind of exposed to the environment. And one thing here on is the testing of the mirrors. On the left side we see the results from the laboratory, and on the right side we see a small white speck that indicates that the wave front of the light that is coming to the cells has an error of almost 1 micrometer, and this is due to an impact of a micrometeoroid. Only a few micrometer in size with a few kilometers per second leads to this kind of damage, because these particles, they are maybe tiny, 5 microns, 10 microns, 100 microns, but they fly with around 15 to 70 kilometers per second. And this is like a bullet, causing a lot of damage, as you've seen it in the solar cells. And that's the reason why we need to understand the meteor streams. That's also the reason why we are conducting all this research, to understand the dust vicinity of our home planet, and also to really create something for risk assessment and mitigation for spacecraft, and also for interplanetary flight and what have you, because these are real threats and risks, to be honest. So this is the reason why we do this research, and also try to build a dust model. And this is also something I'm working on in my academic work now. Speaking of the direction, even without a stereoscopic camera, also without the need to do this, even when you're going outside, you can determine where they are coming from. You just need to stack the meteors into one image and see where they're coming from. So if you follow the lines back, you will see that they are coming from a certain dedicated direction. It's called the radiant. And the radiant, you can imagine like sitting or driving with your car while it's snowing, and the snow is falling vertically down without any wind or so. If you drive, you see how the snow is coming in front of you, and it seems that they are all coming from a certain direction, and this direction is the radiant, like an effect, so to speak. But talking about the rate of meteors, I would like to cover now some mathematical equation with you. And this equation is very important because it is, first of all, it has a nice name, the zenithal hourly rate, but most importantly is that when you are reading the news or so about meteor rates and so on, you always read the ZHR. Yeah, something like, oh, we have the Geminids, 120 meteors per hour, so you can see 100 per hours here and there. And people later get frustrated because they didn't see so many meteors. So how can this happen? Now, this is the ZHR. It's a value you will get from the newspapers or from the media or from the internet. But what you really want to have is the HR, the hourly rate, the rate you will perceive as a human being. Now, this is a small task for you to put all the equation to the left side. So HR stands alone, but I think it's kind of simple. You multiply with the sinus HR, whatever this is, and divide it by F times R, and then this exponent. But let's go through the equation step by step, and you will understand why we will see less meteors than originally anticipated. We want to have HR, right? And the ZHR is, for example, for the Geminids, 120. Now, the first thing, of course, is when we multiply with sinus HR, what is this? Well, it is the height of the radiant above the sky, the horizon. So for example, here in this case, the radiant, if it's at the zenith, then this lower part is 1. Perfect, no correction factor. But if the radiant is only 60 degrees above the horizon, which is also a lot, then the sinus of 60 degrees is 0.5, 50%, which means that the zenithal hourly rate of 120 is already dropping to 60. Just because of the fact that the radiant is at 60 degrees. Yeah, that's it. The other factor is the F factor, and the F factor is pretty simple. Yeah, it's the value K simply indicates how many percentage of the sky you can see with your eyes. So for example, you'll sit there, you see, okay, with my eyes I can only cover, let's say 70%. Then I have maybe a few clouds here and there, so maybe let's say 65%, so 0.65. And this is another correction factor that reduces effectively the observational field. The last thing here is related to the meteor stream and also to the conditions where you're observing. So what does it mean? R is the so-called population index, and it indicates what is the percentual relation between larger meteors and smaller meteors in this particular stream. You know, for let's say some streams have one large meteor and also one faint meteor. Others have maybe one large and 5 faint, so a different relation between the different sizes. And this R value is for most meteor streams at around 2. For the Geminids, I think it's 2.5. LM is the limiting magnitude. So what is the faintest star you can see in your vicinity? If you are in the desert, then you can even see stars with which are faint as 6.5, which means that this factor here is 1. On the other side, it's not here, it's on the it's divided by ZHR is divided by R to the power of 6.5 minus LM, which means if you're in the city where the faintest star is maybe 4.5, yeah, then you have maybe 2 to the power of 2, which is 4, and then you have to divide the number again by 4, for example. So, for example, I don't know, a zenithally hourly rate of 80 is reduced to then 20. Then with the radiant only at 60 degrees, it then decreases to only 10. So please be aware of that and compute this by our own. I think this is a good task for you on a piece of paper or maybe for another video using Python code. This is an instrument. And why? Well, we will talk about this later. Keep it in mind. Keep this picture in mind, and I will talk about this later when we go to Universe Sandbox. But first of all, I would like to move now to Stellarium. And here in Stellarium, I would like to have a look at Geminids. So I just opened it. Today is the 6th of December. And as I said, on the 14th at around midnight, we have, the peak more or less. The other important thing about the ZHR is that the ZHR is not a value that is there for the entire night. It's maybe only an hour where the maximum applies. So you have to be also aware of this factor as well. Now we have like here at around 3 a.m. the moon is already coming out of the horizon, so it also reducing the visibility even more. Let's go to 2 a.m. and let's turn on the constellations. And here we have the Geminids, we have Jupiter, and here is the radiant of the Geminids. Now let's turn on the where is it? The azimuthal grid, which indicates how many degrees we are above the horizon. And here at this particular time, the Geminids are at around 75 degrees almost. So yeah, more than half. So less than half of the ZHR need to be reduced. And here are all the factors. So overnight, all the Geminids are coming basically from this virtual direction. It also applies for the other meteors as well. And all of them of the streams have the certain direction. And why is it? Well, based on all the observations, we can create some kind of simulations like we have it here from meteorshowers.org. Now here we see the proceeds, but we can also go down and have a look, for example, at the Geminids mid of December, and where we see that the stream is here at this time crossing the Earth's orbit, coming from the night side. We see it's a little bit inclined, so we do not have any Geminids from the other direction that we could see theoretically from day side, but there are certain streams where you see the streams twice a year from the day and night side. From night side, it's good for us. We see them with the naked eye camera system and what have you. But from the day side, we need radio systems to detect, because the sun is disturbing, of course, we don't see the meteor streams. And with the radio, it works because when a meteor goes through the atmosphere, it creates an ionized channel of air. And this ionized channel, you can imagine like a big reflector for radio waves. So we hear some kind of pings in our radio signals, and this indicates that a meteor was just crossing in our or entering our home planet. The cool thing about this tool here is we can also plot everything at once. This looks insanely cool, I have to say, but it also eats a lot of resources, so your laptop will probably get a little bit warm. And you may ask yourself, whoa, this is crazy, all the streams, they are crossing Earth, right? So this has to mean something. Well, what you see here is called an observational bias, because an observational bias leads exactly to this kind of conclusion where you say, hey, all the dust streams, they are hitting Earth. No, they hit Earth because we observe them, and of course we can only observe them when they are crossing the Earth's orbit, right? And of course, if you would zoom out and you would see all the dust streams, it would probably be covered by tons of different streams. And this is the task of the simulation software I'm also working with at the university to get a better understanding of how dust is distributed in the cosmos, because this is really important and has technical implications for for space missions, right? Let's also increase it maybe a little bit, and it's so mesmerizing. That's so cool. Anyway, I'm playing it a little bit too much. I would say let's stop it for here. And let's continue with the second part of the video. Okay, we are here now in Universe Sandbox. You see, I just disappeared. I'm now on my Windows operating system, and I forgot to mount my green screen. So yeah, instead of leaving my background here unblurred, I would say, let's get rid of my appearance. Anyway, this is the default loading screen of Universe Sandbox AU, as you may know. We have here the menu, and I would suggest we click here on open, and in the search bar we search for something called asteroids. And here we have different options to choose from, and we go here for the potentially hazardous asteroids. Please don't be confused or afraid of what you will see. This naming is an artificial naming of these objects when they fulfill certain requirements. Maybe something we will cover in the future video, but nothing to be afraid of for now. We have here the Earth revolving. It's a very chaotic situation. And one of the objects we can search is 3,200 Phaethon. Now Phaethon is here. There it is. Let's click on Phaethon. It's very difficult to see something in this chaos. And there we are. Some kind of inclined orbit, so not within the ecliptic plane. Here's the Earth. And let's also show us the path of Phaethon. And Phaethon is revolving here around the sun. And the thing is, it's going far away, but it's also approaching the sun very, very closely. So it's almost, you see, wow, it's way closer than Mercury. And this is pretty impressive. We can go here to the motion settings, for example, see what kind of semi-major axis and properties we have. And we see here the pericenter distance is 0.14 astronomical units. That corresponds to 18 million kilometers. Now the thing about Phaethon is that there are like different effects that cause cosmic dust. Of course, collisions, right? Collisions between asteroids, between meteoroids, or also an impact of an asteroid on the moon causes some dust. These are all the effects that lead to cosmic dust. This is the one thing. The other thing is, of course, comets. Yeah, you may have heard about the comets or even seen one where the ice, it's like a frozen ice ball that heats up when it comes closer to the sun. It gases out and provides a lot of different ice particles, dust particles, and so on. But the other object or the other effect that leads to cosmic dust is also by objects that are rather unknown, like this object here, 3,200 Phaethon, because on the one side it behaves or looks, let's say, like an asteroid. On the other hand, it behaves a little bit like a comet. And the thing is, we call these objects active asteroids. And these active asteroids, they provide us with dust, probably by thermal cracking and also other effects I don't want to cover here now in this video. But Phaethon is an object of very strange behavior. Now, if you recall the video, the slides I just showed you in the beginning, you may recall this small satellite I just showed you. And this is the mission of Destiny Plus from JAXA that will actually fly to Phaethon in the flyby mission and see what's going on there. And the cool thing is that now back in academia, I'm actually literally working on this mission. So I will have also my stake there and hopefully help humanity to gain some insights with scientific analysis. Also something for the future. Long story short is, I would say, on between the 13th and 14th of December in the night, go outside, have a look there. And if you really want to see whether it's worthy or not, I would suggest to have a very last view on a certain website. So let's finish here with Universe Sandbox and go to our last resource. Here on globalmeteornetwork.org/flux, we see currently, considering different observations, the number of meteors, the visual zenithly hour rate in the next 24 hours, which is currently now at around 34. Now, as I said already, this considers all the different things. Everything below 30 is considered as sporadic, but now the line will probably increase during the next days because of this peak we see here, the Geminids that will peak now soon. So we have here this slope that's currently increasing, and this is also a little bit the reason why the numbers are increasing now. We have here also other values here from different meteor showers and so on. But let's cover this for maybe a Python project, for a coding project. Here today, I just wanted to give you some scientific insights and ideas about meteors, and I hope you enjoyed it. I hope you learned something, and if you have any ideas, I would suggest let's have a look at this next time. The next video will be with some Python coding, and then I will cover some meteor topics there. Until then, have a nice day and see you next time.